Hello there, and welcome to Sleepy Science Vault. Somewhere above you, right now, hanging quietly in the dark, there is a galaxy. 200 billion stars, give or take, turning slowly together in a vast spiral of light and dust. You know it as the Milky Way. You have lived inside it your entire life, on a small rocky planet tucked into one of its outer arms, and you have probably never thought of it as something with a lifespan. A beginning. A middle. And somewhere, far off in the deep future, an end. Tonight, we are going to talk about that end. Not with fear, and not with urgency, because none of this is urgent. Nothing we are about to describe will happen in your lifetime, or in the lifetime of your children, or your children's children, 1,000 generations from now. This is a story that unfolds across billions of years, so slowly that it barely qualifies as a story at all in human terms. It is more like a very long, very quiet exhale. So let yourself settle in. Let your thoughts slow down to galactic time, where 1,000,000 years is barely a heartbeat, and let's begin. The Milky Way is dying. Not violently. Not suddenly. There will be no explosion, no dramatic collapse, no single moment you could point to and say, that's when it happened. Instead, our galaxy is fading the way a fire fades after the wood runs low, gradually, gently, one ember at a time, until one day there is only warmth left, and then, eventually, not even that. To understand how a galaxy dies, we first have to understand how a galaxy lives. And a galaxy lives, in the most fundamental sense, by making stars. Stars are born out of clouds of gas, vast, cold, drifting reservoirs of hydrogen that stretch across hundreds of light years, waiting patiently in the dark. Under the right conditions, gravity pulls these clouds inward. They collapse. They compress. They heat up. And at the center of that collapsing cloud, if enough material gathers, nuclear fusion ignites, and a new star is born. This has been happening in the Milky Way for over 13 billion years. Cloud after cloud, generation after generation, star after star, spinning quietly into existence in the vast dark between the older ones. But here's the first fact we want to sit with tonight. The foundation for everything else we'll explore in this segment. The Milky Way is gradually using up its supply of cold gas. And that cold gas is the raw material needed to make new stars. Think of it like a fire that has been burning for a very, very long time. At first, there is fuel everywhere. Endless supply. The fire burns bright and fast, consuming as much as it wants, whenever it wants. But fuel, even in a galaxy, is not infinite. Every star that forms uses up a portion of that reservoir. Every collapsing cloud takes gas that will never return to the reservoir in quite the same form again. Slowly, imperceptibly, the supply diminishes. This is not something that happens overnight, or over a century, or even over 1,000,000 years in any dramatic way. Galactic gas reservoirs are almost incomprehensibly vast. But vast is not infinite. And after billions of years of steady consumption, even a supply that vast begins to thin. This brings us to our second fact. As that gas supply shrinks, something interesting happens. star formation does not stop all at once. It slows down. This matters more than it might seem at first. A dramatic ending would almost be easier to picture, a galaxy blazing brightly and then abruptly going dark, like a candle snuffed out in a single breath. But that is not what is happening to the Milky Way, and it is not what happens to most galaxies as they age. Instead, there is a long, slow tapering. Fewer clouds reach the density needed to collapse. Fewer collapses produce stars massive enough to shine brightly. The rate of birth declines, year after year, era after era, the way a river might slow as it nears a wide, flat delta, not stopping, just spreading thinner, moving slower, quieter with every passing mile. And that leads us gently into our third fact tonight. The Milky Way still forms new stars, even now, even today, somewhere in its spiral arms. A cloud of gas is collapsing this very moment. But it does so at a rate that is modest compared with its past. This is why astronomers describe the galaxy as being in a long decline, rather than facing any kind of sudden collapse. There is no galactic catastrophe waiting around the corner. Just a graceful, unhurried winding down, the kind that takes billions of years to notice at all. It's worth pausing here, in this quiet moment, to really absorb that. The Milky Way is not falling apart. It is not breaking. It is aging, the way a person ages, the way a tree ages, the way anything with a long life eventually settles into a slower, gentler rhythm than it had in its youth. There is something almost peaceful in that image, isn't there? A galaxy easing into its later years, still glowing, still turning, still cradling its 200 billion stars, just a little quieter than it used to be. Now, our fourth fact adds an important layer of understanding to everything we've discussed so far. The Milky Way's decline is tied specifically to the exhaustion of star-forming gas, not simply to the aging of its existing stars. This distinction matters more than you might think. Stars, individually, do age and die, some quickly, in a blaze of supernova light, others slowly, fading over tens of billions of years. But the galaxy's overall decline isn't primarily about its current stellar population getting old. Old stars can keep shining for a very long time. The real story, the deeper story, is about supply. It's about whether there is enough raw material left to build the next generation of stars, and the generation after that, and so on. A galaxy can have plenty of stars and still be dying, in the sense that matters here, if the ingredients for making new ones are running low. It's a bit like a great library that has been passed down through generations. The books already on the shelves are still there, still readable, still full of light, but if no new books are being written, if the presses have gone quiet, the library itself is entering a different chapter of its existence. Not empty. Not gone. Just no longer growing the way it once did. Let's move now to some numbers, quiet, precise numbers that help us understand exactly where the Milky Way stands today in this long process. Fact number 5 tells us that the Milky Way currently forms only about 7 new stars per year. 7. Just 7 new stars, across an entire galaxy, in an entire year. Sit with that for a moment. 7 new points of light, born somewhere among 200 billion existing stars, over the course of 365 days. It sounds small, and in a way, it is. For a galaxy of the Milky Way's size and mass, this is considered a modest rate, nowhere near what it once achieved in its youth, when star formation proceeded at a much faster pace, when new suns ignited far more frequently across its spiral arms. And yet, 7 stars a year, over a century, over 1 million years, still adds up to something remarkable. 1 million years is nothing, cosmically speaking, barely a breath, and even in that nothing span of time, 7 million new stars might come into being. So even in decline, even in its quieter years, the galaxy is still creating, still breathing life into the dark. Just slowly, patiently, without the urgency of its youth. This modest birth rate is a direct symptom of everything we discussed earlier: the shrinking reservoir, the thinning fuel supply. And that brings us to a genuinely striking figure, one that puts the entire scale of this decline into sharp focus. Our sixth fact tonight: some estimates suggest that the Milky Way has already used about 90% of its hydrogen fuel for star formation. 90%. Let that settle for a moment in the quiet. If you imagine the entire reservoir of star-forming hydrogen the Milky Way was born with, the raw material that fueled billions of years of stellar creation, that built every star you can see in the night sky, every star that built the elements inside your own body, 9/10 of that reservoir has already been spent, used, transformed into stars, some of which lived and died long before the Earth itself existed. What remains is a kind of ember, a remaining tenth. Still enough to keep forming stars for a long time yet, still enough for that gentle 7 per year trickle to continue for ages into the future. But it is undeniably the smaller portion of what once was. The Milky Way, in this sense, is not in its youth, or even its middle age. It is somewhere further along, in the long, unhurried autumn of its life as a star-forming galaxy. Fact 7 echoes and reinforces this same number, because it is worth hearing twice, in different words, so that it settles properly into the mind before we move forward. Astronomers estimate that the Milky Way has consumed roughly 90% of its original hydrogen supply for star formation. This is not a fringe idea or a single outlying calculation. It reflects a broader understanding, built from careful observation and modeling, of just how far along our galaxy is in this long, slow process of using up what it was given. It is strange, in a way, to think of a galaxy as having been given something at all, as though it started with an inheritance, a certain fixed amount of raw material, and has been spending it, generation of stars by generation of stars, ever since its formation billions of years ago. But that is, in essence, exactly what happened. The Milky Way formed with an enormous but finite supply of primordial hydrogen and gas drawn in from its surroundings. And across the long arc of cosmic time, it has been converting that gift, slowly, unevenly, sometimes in great bursts and sometimes in quiet trickles, into starlight. Now, you might wonder, if there is still hydrogen left, why is star formation so modest right now? Why only 7 stars a year, if 1/10 of the original supply still remains? 10% of an enormous number can still be an enormous number, after all. This is where our next few facts take us somewhere deeper, somewhere less about simple arithmetic, and more about the physics of gas itself. Because it turns out that having gas, and having gas that is able to form stars, are not always the same thing. Fact 8 tells us that one reason galaxies die is that their gas can be heated, or otherwise prevented from cooling, so that it cannot condense efficiently into new stars. This is a subtle but important idea. Star formation requires cold gas, cold, dense, quiet gas that can collapse under its own gravity without being pushed apart by heat or turbulence. Hot gas resists collapse. It moves too quickly, too energetically, spreading out instead of pulling inward. So even if a galaxy technically still contains gas, if that gas is heated, by radiation, by shock waves, by energetic events within the galaxy, it can become effectively unusable for star birth. It is there, but it is, in a sense, locked away. Present, but not participating. Imagine a vast field of unlit kindling, damp with rain, unable to catch a spark no matter how much of it there is. The wood is present. The potential fire is present. But without the right conditions, it simply sits there. Silent. Unlit. This single idea reshapes how we think about a galaxy's decline. It is not only about running out of raw material in the simplest sense, it is also about whether the remaining material is in a state that allows it to do what it once did so freely. And this leads us into fact 9, which introduces a word astronomers use quite often when discussing galaxies like our own, the word quench. Some researchers believe that galaxies can be quenched, meaning their star formation is shut down or dramatically suppressed, even before they fully run out of gas. Quenching. It's an evocative word, isn't it? Like a flame being smothered rather than simply burning out on its own. And it captures something important about how galaxies age. A galaxy doesn't necessarily need to use up every last drop of its gas to stop forming stars in any meaningful way. Various processes, heating, turbulence, the loss of gas to outflows, changes in the galaxy's structure over time, can suppress star formation well before the reservoir is truly empty. The fire can go quiet long before the fuel is gone. And this brings us, gently, to our 10th and final fact for tonight's segment, one that ties everything we've discussed into a single, coherent picture of where the Milky Way currently stands. The Milky Way's own decline is connected to this process of quenching, the gradual shutting down of star formation, even before all of its gas is completely exhausted. So here's the fuller picture, the one we've been slowly assembling together across this segment, fact by fact, like pieces of a great, slow-moving mosaic. The Milky Way is not simply running dry, the way a well runs dry after too much water has been drawn from it. It is something more layered than that. Yes, it has used up the vast majority of its original hydrogen, roughly 9/10 of it, gone into stars already born and stars already died. But even the portion that remains is not behaving quite the way it once did. Some of it may be heated, or disturbed, or otherwise prevented from collapsing as freely as it once did in the galaxy's more vigorous youth. The result is a galaxy easing toward quiet, not through sudden emptiness, but through a combination of dwindling supply and gradually suppressed potential. This is what it means, astronomically, for a galaxy like the Milky Way to be dying. Not an ending in the dramatic sense. Not darkness falling all at once. But a long, slow quieting, a graceful transition from a galaxy bursting with new stars, to one that still creates, but sparingly, thoughtfully, almost, the way an old and patient hand might light just one candle, when once it lit 100 without a second thought. And it is worth remembering, as we drift toward the end of this first hour together, that this process is playing out on a timescale almost impossible for a human mind to hold on to. Billions of years have already passed since the Milky Way's most vigorous era of star birth. And billions more will pass before this slow decline reaches anything resembling a true end. You, and everyone you have ever known, exist within a single, brief, brilliant flicker inside a much longer story. A story that began long before the Earth formed, and will continue long after the sun itself has faded into a quiet white ember. There is no reason to feel unsettled by any of this. If anything, there is something quietly comforting in it. The galaxy above you tonight, filled with its 200 billion stars, its slow spiral arms, its ancient reservoirs of hydrogen, is not falling apart. It is aging, the way old and beautiful things age, unhurried, dignified, still glowing softly against the dark, still capable, even now, even after all this time, of bringing something new into being. In our next hour together, we'll continue this journey through the Milky Way's long decline, exploring more of what astronomers have learned about the forces shaping its future, and what this slow fading might ultimately mean for a galaxy that has called itself home to stars, and worlds, and quiet listeners like you, for longer than almost anything else you could imagine. For now, let the thought of that vast, slowly dimming spiral settle over you gently, turning above you in the dark, patient, unhurried, still shining. Let's continue where we left off, and widen our view a little, because the story of the Milky Way's slow fading is not really a story that belongs to the Milky Way alone. It turns out our galaxy is part of something much larger. A pattern. A trend that stretches across billions of galaxies, spanning nearly the entire observable universe. And once you understand that pattern, the Milky Way's gentle decline starts to feel a little less like an isolated event, and a little more like part of the natural rhythm of everything around us. The slowdown in star formation we've been discussing is part of a much broader cosmic trend. Star birth across the entire universe has been declining for billions of years now. This is worth letting sink in for a moment. It is not just our galaxy that is easing into a quieter phase of its life. Galaxies everywhere, spirals like our own, ellipticals, dwarf galaxies scattered through the void, vast clusters bound together by gravity across unimaginable distances, nearly all of them are experiencing some version of the same gradual slowdown. The universe, as a whole, is producing fewer new stars today than it once did. Fewer bright nurseries igniting in the dark. Fewer young, blue-white stars blazing to life in the spiral arms of countless galaxies. Astronomers have been able to measure this by looking deep into the past. Because light takes time to travel, looking far away is the same as looking back in time, and by studying galaxies at different distances, astronomers have essentially built a kind of cosmic timeline, showing how the rate of star formation across the universe has changed, era by era, going all the way back to a time when the universe itself was young. And what that timeline reveals is fact number 12. Star formation across the universe reached its peak long ago, and has been declining ever since. This places the Milky Way's fate within something much larger than itself, a wider cosmic slowdown that touches nearly everything. There is something quietly humbling about this. We often think of the Milky Way's aging as something unique to us, a slow personal decline happening to our particular galaxy, in our particular corner of the universe. But it turns out this is simply what galaxies do, over long enough timescales. There was an era, billions of years ago, when the universe as a whole was far more vigorous, far more prolific, in the business of making stars. Gas was more abundant, and more of it was cold and ready to collapse. Galaxies were closer together, on average, and interactions and collisions between them stirred up gas and triggered new bursts of star formation more frequently. It was, in a sense, the universe's youth. A period bursting with creative energy. That period is now behind us. And it has been behind us for a very long time. Our 13th fact adds a bit more precision to this picture. This universal decline in star formation appears to have been especially steep over the last 9 billion years. 9 billion years. To put that into perspective, the universe itself is roughly 13.8 billion years old. Which means that for nearly 2/3 of the entire history of the universe, star formation has been on a fairly steady downward slope. Not a slope with sudden drops or dramatic cliffs, but a long, gradual decline, like a great tide slowly receding from a shore it once covered completely. 9 billion years ago, the universe was already past its most vigorous star-forming peak, and it has been settling, gradually, into quieter and quieter eras ever since. We happen to exist in one of those quieter eras. Not the quietest it will ever be. There is still a very long future ahead, full of stars yet to form, but quieter, undeniably, than the universe's fiery youth. This brings us to a thought that is genuinely beautiful, if you sit with it for a moment. Fact 14 tells us that astronomers often describe the universe as having already passed through its golden age of star formation. Which means the Milky Way may currently exist in a later, less active phase of cosmic history altogether. A golden age. It's a poetic phrase for astronomers to use, and yet it fits so naturally here. Picture it, billions of years ago, across countless galaxies, stars were forming at a pace far beyond anything happening today. Vast stellar nurseries glowing with newborn light. Galaxies bursting with young blue stars, burning hot and fast. It must have been, in a very real sense, one of the most luminous chapters the universe has ever known. And it has already passed. We are living, right now, in the long afterglow of that golden age. Not in darkness. There is still starlight all around us, still new stars being born, including that gentle trickle of about 7 per year here in the Milky Way, but in a dimmer, more contemplative chapter of the universe's long life. A little like arriving at a grand celebration just after its most brilliant hour, when the music has softened, and the lights have lowered, and what remains is no less meaningful, but undeniably, quieter. So why does this happen? Why would the entire universe experience this same kind of gradual quenching that we discussed with the Milky Way specifically? Fact 15 offers one compelling piece of the answer, and it connects directly to something vast, something almost impossible to fully picture: the expansion of the universe itself. One proposed reason galaxies like the Milky Way eventually fade is that the expansion of the universe makes it harder for hot gas to cool and collapse into new stars. This is a wonderfully strange idea when you really think about it. The universe is expanding, every galaxy, on average, drifting further from every other galaxy, the very fabric of space itself stretching outward in every direction. And that expansion doesn't just separate galaxies from one another. It may also affect the gas within galaxies, and the gas that surrounds them in vast, diffuse halos. As the universe expands, the density of gas throughout the cosmos, on average, continues to decrease. Gas that might once have been drawn together relatively efficiently, cooling and condensing into new stars, now has to travel further and work harder against the backdrop of an ever-thinning, ever-stretching universe. Hot gas surrounding galaxies takes longer to cool, longer to gather, longer to collapse into the tight, cold clouds needed for star birth. And so, gradually, across billions of years, this vast expansion works quietly against the process of star formation almost everywhere, adding yet another layer to why galaxies like our own are easing into quieter phases of their lives. It is a strange kind of symmetry, isn't it? The very thing that gave the universe room to exist, room to grow, room to become the vast and star-filled place we know, is also, slowly, gently, working against the very process that filled it with light in the first place. Now, let's bring our attention back home, back to the Milky Way itself, and to a story that stretches back almost to the beginning of time. Fact 16 tells us that parts of the Milky Way's thick disk began forming about 13 billion years ago. Which means our galaxy contains stellar populations from its very earliest eras, ancient light, quite literally, still shining in our sky today. 13 billion years. Let that number settle for a moment. The universe itself is only slightly older than that. Which means that some of the stars in the Milky Way's thick disk are almost as old as time itself, formed when the universe was still finding its shape, still assembling its first galaxies out of the raw material left over from the Big Bang. And fact 17 sharpens that picture even further. The Milky Way's thick disk began forming only around 800 million years after the Big Bang. 800 million years. In cosmic terms, that is remarkably early, a mere eye blink after the universe itself came into being. It means the Milky Way, in some early form, was already beginning to take shape while the universe was still, in a very real sense, brand new. Long before the sun existed. Long before the Earth existed. Long before almost anything you could name in the night sky today existed in its current form, the earliest structures of our galaxy were already quietly assembling themselves out of primordial gas and the universe's first generations of stars. There is something deeply moving about this, if you let yourself feel it. When you look up at the night sky, some of what you're seeing isn't just old, it is ancient, in the truest sense of the word. Fragments of light and structure that trace their origins back to a time almost unimaginably close to the very beginning of everything. But the Milky Way's long history has not been a gentle, uneventful one. Fact 18 reminds us of that clearly. The Milky Way has not had a peaceful history. Over the course of 13.6 billion years, it has collided with, and absorbed, multiple smaller galaxies. Collided. It's a dramatic word, and in cosmic terms, it's an accurate one. Our galaxy, for all its serene beauty when we look up at it on a clear night, has actually lived a remarkably eventful life. Over billions of years, smaller galaxies, dwarf galaxies, star clusters, streams of gas and stars bound loosely together by their own gravity, have drifted too close to the Milky Way's immense gravitational pull and been drawn in. Pulled apart. Absorbed. Their stars folded into our own galaxy's structure, their gas mixed into our own reservoirs, their entire identities gradually dissolved into the larger whole of the Milky Way itself. This is, in fact, one of the primary ways galaxies like ours grow over cosmic time. Not through some smooth, steady accumulation, but through these dramatic, sweeping encounters, galactic collisions playing out across hundreds of millions of years, each one leaving its mark on the structure we see today. Fact 19 tells us just how eventful this history has truly been. Astronomers have mapped at least 6 ancient merger events in the Milky Way's past. 6 separate occasions, at least, where another galaxy, smaller, but still substantial, crossed paths with our own, and over time, became part of it. 6 moments in this immense span of time when the Milky Way's story intertwined with the story of some other galaxy entirely, absorbing its stars, its gas, its history, into our own. Astronomers have been able to reconstruct these ancient events by studying the motions and chemical compositions of stars throughout the galaxy today. Because remarkably, stars that originated in a galaxy long since absorbed often still move together, still share subtle chemical fingerprints that set them apart from stars born natively within the Milky Way. It's a bit like archaeology, but written in light and motion instead of stone and soil, astronomers carefully piecing together the layers of our galaxy's past, merger by merger, each one a chapter in a long and surprisingly turbulent history. And of all these mergers, one in particular stands out as especially significant. Fact 20 brings us to it directly. The Gaia Enceladus, sometimes called the Sausage Merger, was one of the most important events in the Milky Way's entire history, and it helped build the galaxy's inner halo. This merger, named in part after the Gaia space telescope that helped astronomers discover it, involved a galaxy roughly the size of a small satellite galaxy, substantial, but still much smaller than the Milky Way itself, merging with our galaxy somewhere in the range of 8 to 11 billion years ago. The stars from that ancient, absorbed galaxy didn't simply vanish. They remain here, today, woven into the structure of the Milky Way's inner halo, still moving along orbits that echo the shape of that ancient collision, still carrying, in their chemical composition, evidence of a galaxy that no longer exists as a separate entity at all. If you could somehow trace the paths of enough stars around you tonight, some of them, unknowingly, would lead back not to the Milky Way's own original formation, but to this other galaxy entirely. A galaxy that crossed paths with our own billions of years ago, and in doing so, became a permanent, quiet part of who we are. There is something remarkable in that thought. The Milky Way, this vast structure we call home, is not simply one continuous, unbroken story. It is, in many ways, a gathering of stories, older galaxies, absorbed and woven together over billions of years, their light and their history becoming inseparable from our own. Ancient stars from a galaxy long gone, still shining quietly above you, right now, indistinguishable at a glance from stars that formed here from the very beginning. We've traveled a long way in this segment, from the universe's grand and gradual slowdown in star formation, all the way down to the Milky Way's own ancient and surprisingly turbulent history of growth through collision and absorption. It's a lot to hold in the mind at once, and there's no need to hold on to every detail. Let it settle instead as a feeling, a sense of vast time, vast change, and a galaxy that has lived through far more than its calm nighttime appearance might suggest. In the next part of our journey together, we'll continue exploring this deep history, following the threads of these ancient mergers a little further, and beginning to look at how all of this, the fading gas, the ancient collisions, the long cosmic decline, connects to where the Milky Way is heading next. For now, let it rest quietly in your mind, a galaxy built not just from its own original material, but from pieces of other galaxies entirely, gathered slowly, gently, across billions and billions of years, still turning above you in the dark. Let's return now to that ancient collision we touched on a moment ago, because there is more to uncover in it, more layers to peel back, and it turns out this single event may have shaped the Milky Way more profoundly than almost anything else in its long history. A major merger, occurring roughly 11 billion years ago, helped shape the Milky Way's structure in ways that are still visible today, and contributed directly to the formation of what astronomers call the thick disk. 11 billion years ago. The Milky Way was still young then, still forming its basic architecture, still figuring out, in a sense, what kind of galaxy it was going to become. And into that early, formative period came this other galaxy, smaller, but still substantial enough to leave a permanent mark. Its arrival wasn't a gentle passing. It was a genuine collision, gravitational forces tangling together, stars and gas swirling into new configurations that would echo forward across billions of years. This event didn't just add new stars to the Milky Way. It fundamentally reshaped the galaxy that was already there. Fact 22 tells us that this same merger likely stirred up the pre-existing disk, and scattered many of its stars into more extended, wider orbits than they had before. Try to picture this for a moment. Before this collision, the young Milky Way already had some kind of disk forming, stars moving in relatively orderly paths, settling into the flattened, rotating shape that spiral galaxies tend to take. Then this other galaxy arrived, its gravity pulling and tugging at everything nearby. Stars that had been moving in calm, close orbits were suddenly perturbed, pushed outward, sent drifting into wider, more elongated paths around the galactic center. It was less like a gentle nudge and more like tossing a stone into still water, watching the ripples spread outward, disturbing everything in their path. The galaxy, quite literally, was reshaped by this encounter. Not destroyed. Not undone. But altered, its structure bearing the fingerprints of this ancient impact for billions of years afterward, fingerprints that astronomers can still detect today in the motions of stars scattered throughout the galaxy. But the story of this merger isn't only about disruption. It's also, remarkably, about creation. Fact 23 tells us that the Gaia Enceladus event brought in a gas-rich galaxy, and that this influx of fresh gas triggered a burst of star formation in the young Milky Way. This is worth sitting with for a moment, because it reveals something beautifully paradoxical about cosmic collisions. They can be destructive and generative at the very same time. The incoming galaxy wasn't empty. It carried with it a substantial reservoir of its own gas, and when it merged with the Milky Way, that gas didn't simply vanish or scatter uselessly into the void. Much of it mixed with the Milky Way's own gas, adding fresh fuel to the galaxy's star-forming reservoir. And with fresh fuel came fresh stars. A burst of newly formed stars, born not despite this violent encounter, but directly because of it. There's something almost poetic in that. An event that scattered and disrupted the galaxy's existing structure also, simultaneously, gave it the material to build something new. Destruction and creation, arriving together, inseparable, in the same ancient moment. Of course, this doesn't mean the collision was without cost. Fact 24 brings us back to the more disruptive side of this story. That ancient impact also damaged the Milky Way's protodisk, its early, still-forming disk structure, and pushed a large fraction of its stars outward, toward what would eventually become the galactic halo. The halo is that vast, roughly spherical region surrounding the flat disk of the galaxy, sparsely populated with older stars, stretching far beyond the bright, busy plain where most of the Milky Way's stars and gas reside today. And a significant portion of what now populates that halo traces its origin back to this exact moment. Stars that were once part of the Milky Way's forming disk, gently orbiting close to the galactic plane, were pushed outward by the gravitational chaos of this merger, flung into the wider, quieter orbits of the halo, where many of them still drift today. It's a strange thing to consider, that some of the stars occupying that faint, extended halo around our galaxy aren't foreign visitors from some absorbed galaxy at all, but are, in a sense, refugees from the Milky Way's own early disk. Displaced not by leaving the galaxy, but by a violent reshaping from within, billions of years ago. So what happened next? After this disruption, after this burst of new star formation, after stars were scattered outward into the halo, what became of the Milky Way's disk itself? Fact 25 offers a beautifully clear answer. After that merger, fresh gas gradually settled into a thinner disk, and this new, thinner disk became the primary site of later star formation in the galaxy. Picture the aftermath, slowly unfolding over hundreds of millions of years. The chaos of the collision begins to settle. Gravity, patient as always, begins reorganizing the disrupted material into a more stable configuration. And the gas, the fresh gas brought in by the merger, mixed with what remained of the galaxy's own reservoir, begins settling into a new, flatter, thinner disk than the one that existed before the collision. This thin disk is, in many ways, the structure most people picture when they imagine a spiral galaxy, the bright, star-filled plane where the majority of a galaxy's ongoing star formation typically takes place. And in the Milky Way's case, this particular thin disk owes its existence, at least in part, to the aftermath of this single ancient collision. A structure born from disruption, gradually settling into something new, something that would go on to host billions of years of continued star formation. Meanwhile, the older, thicker disk, the one disturbed by the merger, populated by stars scattered into wider orbits, didn't simply disappear. It continued to exist, continued to age, continued, for a remarkably long time, to form stars of its own. Fact 26 tells us that the thick disk kept forming stars for a very long time, before finally, gradually, coming to a stop, about 8 billion years ago. 8 billion years ago. Think about how much time has passed since then. More than half the current age of the universe. And yet, even after this dramatic, disruptive merger, even after being scattered and reshaped, the Milky Way's thick disk continued producing new stars for billions of years afterward, before its own star-forming activity finally, quietly, came to an end. This tells us something important about how galaxies actually evolve. It isn't a single clean event, followed by stillness. It's layer upon layer of activity, disruption, renewal, and eventual quieting, each phase unfolding across almost unimaginable stretches of time. The thick disk had its own long life, its own extended era of star birth, separate from, but connected to, everything that came both before and after it. And this brings us to a fact that reframes much of what we've discussed so far. Fact 27 reminds us that the Milky Way star formation was not simply a smooth, steady decline from a peak to a trickle. Instead, the galaxy formed stars in bursts throughout much of its history. This is an important correction to any overly simple picture we might have built up. It would be easy to imagine the Milky Way's history as one long, gradual slope, vigorous star formation in the beginning, tapering evenly and predictably down to the modest rate we see today. But that's not quite what happened. Instead, the galaxy's history includes distinct episodes, periods of intensified star formation, often triggered by exactly the kind of event we've just been discussing, ancient mergers stirring up gas and triggering bursts of new stellar birth, followed by quieter periods in between. It's less like a candle burning down at a steady, even rate, and more like a fire that flares up occasionally when new fuel is added, a merger here, a fresh infusion of gas there, interspersed with longer stretches of calmer, steadier burning. The overall trend, across billions of years, is certainly one of decline. But the path to that decline was anything but a simple, uniform slope. Deep within the Milky Way today, there remain physical traces of these ancient bursts of activity, remarkable structures that astronomers sometimes describe using a wonderfully evocative phrase. Fact 28 tells us that the galaxy's center preserves what are sometimes called fossil fragments, structures such as Tarzan V, which record earlier generations of star formation that occurred deep inside the Milky Way, long ago. Tarzan V is a genuinely remarkable object, tucked deep within the crowded, dusty central regions of our galaxy. It's a dense stellar structure containing stars from at least two distinctly different eras of formation, ancient populations that appear to have formed separately, at different times, yet now exist together in the same crowded region near the galaxy's core. In a very real sense, it functions almost like a fossil record, preserving evidence of star-forming events that occurred billions of years apart, layered together in one small, dense pocket of the galaxy. It's a beautiful image, isn't it? the idea that buried deep within the bright, busy center of our galaxy, there exist these quiet pockets of ancient history, faithfully preserving evidence of star formation episodes stretching back across enormous spans of time. Fossils, not carved in stone, but written in starlight. Now, with all of this discussion of mergers, and bursts, and dramatic collisions, it would be easy to assume that the Milky Way built most of its mass this way, through these dramatic encounters with other galaxies. But Fact 29 offers an important, grounding correction to that assumption. Even these huge accretion events, these dramatic mergers we've spent so much time discussing, contributed only a fraction of the Milky Way's total growth. Which means the galaxy built the majority of its stellar mass internally, forming stars from its own gas, gradually, over billions of years, rather than primarily through absorbing other galaxies. This is worth appreciating fully. The mergers we've discussed, Gaia and Enceladus, and the other ancient collisions astronomers have mapped throughout the galaxy's history, were undeniably significant. They reshaped the galaxy's structure. They triggered bursts of star formation. They scattered stars into the halo and left fossil records still visible today. But when you step back and look at the bigger picture, the total mass of stars that make up the Milky Way as we see it now, most of that mass didn't arrive from outside. It was built here, internally, through the slow, patient, ongoing process of gas collapsing into stars, generation after generation, largely independent of these dramatic external encounters. It's a nice piece of perspective to hold on to. For all the drama of ancient collisions and galactic mergers, the Milky Way is, at its core, fundamentally a self-built structure. A galaxy that grew primarily through its own quiet, internal processes, with these dramatic mergers acting more like significant punctuation marks in a much longer sentence, rather than the primary substance of the story itself. And finally, to close this segment, Fact 30 brings us back once more to those ancient collisions, and to the traces they left behind. Some of the Milky Way's early merger debris still survives today, within the galaxy's stellar halo, acting as a quiet, enduring record of ancient cosmic collisions, still readable by anyone patient enough to study it carefully. That faint halo surrounding our galaxy, sparsely populated with old, slowly drifting stars, is far more than empty space with a few scattered points of light. It is, in a very real sense, an archive. A record of galaxies that no longer exist as separate entities, their stars still moving along orbits shaped by encounters that occurred billions of years ago. Every so often, astronomers identify a stream of stars within this halo, moving together, sharing subtle chemical similarities, and are able to trace that stream back to a specific ancient merger, a specific galaxy, absorbed long ago, still leaving its quiet signature on the structure of the Milky Way today. We've covered a great deal of ground in this segment, an ancient merger 11 billion years ago that reshaped the galaxy's disk, a burst of star formation triggered by fresh gas, stars scattered outward into the halo, a new thinner disk gradually settling into place, and the slow, uneven, burst-filled rhythm of star formation that followed across billions of years. It's a lot to absorb, and there's no need to hold every detail precisely. Let it rest instead as a broader impression, a galaxy with a far more complicated, far more eventful history than its calm, familiar appearance in the night sky might ever suggest. In our next segment together, we'll continue following this long story forward, moving further through the Milky Way's history, and beginning to explore some of the other forces, near and far, that continue to shape its slow, patient evolution. For now, let this settle quietly. A galaxy built from both its own gas and the remnants of others, scattered and reshaped and renewed across billions of years, still turning gently above you, carrying its ancient fossils and its quiet halo of old stars, into the long night ahead. We left off surrounded by fossils and archives, ancient debris scattered quietly through the Milky Way's halo. Let's continue exploring that archive now, because it turns out it's even richer, and even stranger, than what we've uncovered so far. The Milky Way's halo contains debris from numerous past dwarf galaxy mergers, and this tells us something important. The galaxy's history has already been shaped, again and again, by repeated accretion events, stretching back across billions of years. We tend to think of history as a single line, one event following another in orderly sequence. But the Milky Way's history is more like a series of overlapping layers, each merger leaving its own signature, some faint, some pronounced, scattered throughout the halo like sediment settling slowly over an unimaginably long span of time. And in recent years, astronomers, aided by increasingly precise measurements of stellar positions and motions, have begun identifying more and more of these ancient encounters. Each one adds another thread to the tapestry. One of the more recently identified mergers carries a name drawn from ancient mythology: Pontus. And this event, astronomers believe, may have occurred very early in the Milky Way's history, somewhere between 8 and 10 billion years ago. Pontus. In Greek mythology, a primordial deity of the sea, ancient even by the standards of the old gods. It's a fitting name, in a way, for a merger event that reaches back so deep into the Milky Way's own early history. Because unlike some of the more clearly defined, well-studied mergers we've discussed already, Pontus represents a more recent discovery, a subtler signal, teased out carefully from the motions of stars, hinting at a collision that occurred so long ago it barely leaves a clear trace. And the trace it does leave is a curious one. Fact 33 tells us that Pontus appears to have contributed stars that move slowly, and in a direction opposite to the Milky Way's main rotation. Try to picture that for a moment. Nearly all the stars in the Milky Way's disk, the vast majority of the 200 billion or so scattered throughout our galaxy, orbit the galactic center in roughly the same direction, part of that grand, unified rotation that gives spiral galaxies their elegant, swirling shape. But scattered among them, quietly, almost invisibly, are stars that move differently, slower, and turning the other way, against the flow of everything around them. These retrograde stars, as astronomers call them, are like quiet descenders within the galaxy's otherwise orderly motion. And tracing their origin back to Pontus suggests that this ancient merger, whatever galaxy it once was, arrived at the Milky Way on a path that ran counter to our galaxy's own rotation, its stars still carrying that contrary motion within them, billions of years later, like a memory the galaxy has never quite forgotten. Pontus isn't the only ancient merger to receive such a name. Fact 34 introduces us to another. Sequoia, thought to have occurred somewhere around 9 billion years ago. Named after the towering, ancient trees, Sequoia represents another significant collision in the Milky Way's deep past, one that, like Pontus, has only become clearly identifiable through careful, modern analysis of stellar motion. Astronomers studying the orbits and chemical compositions of stars throughout the galaxy have been able to identify distinct groupings, families of stars that share subtle characteristics, setting them apart from the galaxy's native population, and pointing back toward a shared origin in some other, long-vanished galaxy. 9 billion years is an extraordinary span of time. And yet, remarkably, the signature of this ancient collision remains detectable today, embedded quietly within the motions of stars still orbiting throughout our galaxy. Perhaps the most striking of these newly identified events, though, is the one described in Fact 35. The Kraken event may have been the most massive merger the Milky Way has ever experienced. The Kraken, an old maritime legend, is a creature of almost unimaginable scale, said to rise from the deepest, darkest parts of the ocean. And true to its name, this particular ancient merger appears to have involved a genuinely substantial galaxy, larger, potentially, than any of the other individual mergers astronomers have identified so far in the Milky Way's long history. An encounter of this scale would have left a truly profound mark on the young Milky Way. A significant portion of stars scattered throughout the galaxy's inner halo today may trace their origin back to this single, massive collision, a galaxy so substantial that its absorption fundamentally shaped much of what the Milky Way would eventually become. It's worth pausing here for a moment, letting the scale of this settle. We are talking about entire galaxies, not small clusters of stars, but vast, structured systems containing potentially billions of stars of their own, being drawn in, torn apart, and absorbed into the larger structure of the Milky Way. And the Kraken, if the current understanding holds, represents the largest such event our galaxy has ever endured. Not all of the Milky Way's encounters, though, belong entirely to the ancient past. Fact 36 brings us to a merger that is, in a very real sense, still happening, right now, even as we speak. The Sagittarius dwarf galaxy has repeatedly passed through the Milky Way, disturbing it, again and again, across billions of years. Unlike Pontus, or Sequoia, or the Kraken, all ancient events reconstructed carefully from subtle traces left behind, Sagittarius is a merger astronomers can observe unfolding, directly, in real time. This small galaxy, orbiting close to the Milky Way, has been caught in a long, slow dance with our galaxy for billions of years, repeatedly swinging close, passing through parts of the Milky Way's disk and halo, each pass stretching and disturbing it a little further, before swinging back out and eventually returning again. It's remarkable to consider that this process, so similar to the ancient mergers we've spent this segment exploring, is not confined entirely to the deep past. It is, in its own smaller way, still continuing today, an ongoing echo of the same fundamental process that has shaped so much of the Milky Way's long history. Now, how exactly do astronomers manage to trace all of these ancient events with such confidence? Fact 37 offers an important piece of that answer. Some of the Milky Way's most important merger remnants are traced not simply through the motions of individual stars scattered through the halo, but through globular clusters. Globular clusters are dense, ancient groupings of stars, tens of thousands or even hundreds of thousands bound tightly together by their own gravity, often orbiting far out in a galaxy's halo. And remarkably, many of these clusters appear to have originated not within the Milky Way itself, but within other, smaller galaxies that were later absorbed. Because these clusters are so dense, and so gravitationally bound, they tend to survive the chaos of a merger largely intact, drifting into the Milky Way's halo as a kind of preserved, self-contained fossil, a tight little knot of stars, still holding together, still carrying the chemical fingerprints of whatever galaxy it originally belonged to. By studying these globular clusters carefully, their motions, their compositions, their ages, astronomers have been able to trace many of them back to specific ancient mergers, adding yet another layer of evidence to this slowly emerging picture of the Milky Way's turbulent, accumulated past. And here's where the story becomes especially intriguing, especially open-ended. Fact 38 tells us that astronomers suspect there may still be at least 15 more significant merger remnants, hidden somewhere within the Milky Way's past, yet to be fully identified. 15. At least 15 more ancient collisions, potentially, still waiting to be uncovered, their traces scattered somewhere among the billions of stars that make up our galaxy today. This is, in many ways, an active and ongoing area of research, astronomers continuing to sift patiently through vast catalogs of stellar positions, motions, and chemical compositions, searching for subtle patterns that might reveal yet another ancient encounter, another galaxy absorbed long ago, its identity nearly, but not quite, entirely dissolved into the larger structure of the Milky Way. It's a reminder that even after everything we've discussed, Gaia, Enceladus, Pontus, Sequoia, the Kraken, Sagittarius still passing through even now, the full history of our galaxy remains, in many ways, still being written. Or perhaps more accurately, still being slowly, carefully, read. This leads us naturally into fact 39, and a wonderfully evocative phrase astronomers sometimes use to describe what they're searching for. The Milky Way may contain hidden fossil galaxies, the buried, deeply embedded remains of dwarf galaxies swallowed so long ago, and so completely, that their traces lie hidden deep within the Milky Way's own structure. Fossil galaxies. It's a beautiful phrase, isn't it? Not simply scattered debris drifting through the halo, but entire buried structures, remnants of once independent galaxies, folded so deeply into the Milky Way over such an enormous span of time that uncovering them requires something akin to careful excavation, not with shovels and brushes, but with statistics, spectroscopy, and enormous, painstakingly assembled catalogs of stellar data. And fact 40 brings us to one such candidate, recently proposed, carrying yet another evocative name drawn from mythology. Loki. This newly suggested fossil galaxy, named after the trickster figure of Norse mythology, may represent one of the earliest mergers in the Milky Way's long history, a galaxy absorbed so long ago, and so thoroughly, that its presence has only just begun to emerge from careful analysis, hidden deep within the layered, ancient structure of our galaxy's innermost regions. There's something quietly fitting about that name, isn't there? A trickster, fittingly elusive, hiding in plain sight for billions of years, its true nature only now beginning to be understood. As we near the end of this segment, it's worth taking a moment to simply appreciate the scale of what we've been exploring. Gaia Enceladus, Pontus, Sequoia, the Kraken, Sagittarius, still active even today. And now, potentially, Loki, along with 15 or more other mergers, still waiting, somewhere in the data, to be uncovered. The Milky Way, this galaxy we call home, this structure we so often picture as calm, and settled, and quietly eternal, has, in truth, lived an extraordinarily eventful life. Built, layer upon layer, from its own gas and from the remnants of countless other galaxies, each encounter leaving its own quiet signature, still readable today, billions of years later, in the motions and compositions of stars scattered throughout the sky above you. In our next segment together, we'll carry this exploration further, moving beyond these ancient encounters, and beginning to look at what all of this history means for where the Milky Way is heading, as its long, slow story continues to unfold. For now, let yourself simply rest in the scale of it all, a galaxy assembled from fossils within fossils, from mergers within mergers, from ancient collisions still being uncovered even now, turning quietly above you, patient and unhurried, carrying every one of these buried histories forward into the long night ahead. Let's stay with Loki a moment longer, because the evidence surrounding it offers a wonderful glimpse into exactly how astronomers managed to identify a galaxy that was absorbed so long ago it left almost no obvious trace. Loki's stars show mixed orbital directions, some moving one way, some another. And this, subtle as it sounds, is precisely the kind of clue that tells astronomers these stars did not all form within the Milky Way itself. Think back to what we discussed earlier, how most of the Milky Way's disk stars move together, in roughly the same direction, part of that grand, coordinated rotation that gives our galaxy its shape. When astronomers instead find a pocket of stars with orbital directions that don't quite agree with each other, some prograde, some retrograde, scattered rather than aligned, it acts almost like a fingerprint left at a scene. It suggests these stars didn't originate from a single, orderly process of internal star formation, but were instead gathered together from somewhere else entirely, a separate galaxy, with its own separate history, its stars carrying that history with them even after being folded into the Milky Way. It's a quiet kind of evidence, easy to overlook if you weren't looking closely. But patterns like this, subtle as they are, form the backbone of how astronomers piece together events that occurred so long ago. No direct record of them could possibly remain, except in the motion of the stars themselves. From Loki, let's turn to another buried remnant, one whose imprint on the Milky Way turns out to be surprisingly large. Fact 42 tells us that this remnant, named Heracles, may account for roughly 1/3 of the total mass of the Milky Way's spherical halo. 1/3. Let that number settle for a moment. The halo, that vast, sparsely populated region of old stars surrounding the Milky Way's disk, stretching out in every direction, is an enormous structure in its own right. And if Heracles truly accounts for something close to 1/3 of its total mass, that means a single ancient galaxy, absorbed at some point in the Milky Way's deep past, contributed an extraordinarily large portion of what we now consider to be part of our galaxy's own halo. Named, fittingly, after the legendary hero known for his immense strength, Heracles appears to have been discovered through patterns in stellar motion and composition deep within the galaxy's central and inner regions, a signature so substantial that it couldn't have come from ordinary internal star formation alone. And this brings us to fact 43, a natural and important reflection on what Heracles teaches us more broadly. The discovery of Heracles suggests that a single ancient merger can leave an extraordinarily large, and remarkably long-lasting, imprint on a galaxy. It reshapes, a little, how we ought to think about all of this. We've spent quite some time now discussing numerous mergers. Gaia Enceladus, Pontus, Sequoia, the Kraken, Loki, and now Heracles. It would be easy to imagine each one contributing some small, modest fraction to the Milky Way's overall structure. But Heracles reminds us that this isn't always the case. Sometimes, a single encounter, occurring at exactly the right moment, involving exactly the right mass, can leave a mark so large, so foundational, that it fundamentally shapes an enormous portion of the galaxy we see today, billions of years later. Beyond these large, foundational remnants, though, the Milky Way carries countless smaller traces of its long history too. Fact 44 introduces us to one of the more delicate, more elegant forms this evidence can take. Scientists have found that the Milky Way hosts more than a dozen stellar streams, the long, thin, shredded remains of smaller galaxies and star clusters, torn slowly apart by the Milky Way's gravity. A stellar stream forms when a smaller structure, a dwarf galaxy or a globular cluster, passes too close to the Milky Way, and its stars, no longer able to hold together against our galaxy's immense gravitational pull, gradually stretch out into a long, thin trail. Picture a bit of thread slowly being pulled apart, unwinding into a single loose strand, drifting along an orbit around the galaxy, all its stars still following roughly the same path, even though the structure that once held them together has long since dissolved. More than a dozen of these ghostly ribbons of stars, currently, have been identified drifting through the Milky Way's halo and disk. Each one represents a smaller, gentler echo of the same fundamental process we've spent this whole journey exploring: smaller structures, pulled apart and absorbed, their stars scattered into long, graceful trails across the sky. And these streams span an enormous range of ages. Fact 45 tells us that the youngest known stellar stream likely formed only about 700 million years ago. 700 million years. In the context of everything we've discussed tonight, spanning billions upon billions of years, this is remarkably recent, practically the blink of an eye. Cosmically speaking. It's a reminder that this process of absorption, of smaller structures being gently torn apart and woven into the Milky Way, isn't confined entirely to the ancient past. It has continued, in smaller, gentler ways, right up into what is, relatively speaking, the recent history of our galaxy. Interestingly, though, not all evidence is equally easy to find. Some of the oldest merger remnants turn out to be the hardest to detect at all. Fact 46 offers a lovely explanation as to why. Some of the earliest merger remnants are the hardest to find, because the Milky Way built up inside out, meaning its earliest history is buried, quite literally, deep within its central regions, hidden beneath everything that formed afterward. This idea of building inside out is worth sitting with for a moment. It means that the Milky Way's very oldest structures, its earliest stars, its earliest mergers, tend to be concentrated closer to the galaxy's center, while progressively younger material settled into the outer disk over time. Which means, quite literally, that the deepest layers of the Milky Way's history are buried in its most crowded, most difficult to observe region, the dense, dusty, star-crowded central bulge, where light from more distant stars is often obscured, and where the sheer density of stars makes it far harder to pick out subtle patterns in motion and composition. It's a bit like trying to read the earliest pages of a very old, very thick book, pages that have ended up buried beneath everything written afterward, pressed tightly together at the very center of the volume. The information is there. It hasn't been erased. But reaching it, reading it clearly, requires far more effort than examining the newer pages near the surface. Despite these challenges, though, remarkable progress continues to be made, thanks in large part to a particular space mission that has quietly transformed our understanding of the Milky Way's structure. Fact 47 tells us that new Gaia-based research has uncovered previously unknown merger evidence by studying the motions of globular clusters, stellar streams, and satellite galaxies, all together, as interconnected pieces of a single picture. The Gaia spacecraft, launched to map the positions and motions of well over 1 billion stars throughout the Milky Way with extraordinary precision, has fundamentally reshaped this entire field of study. Where astronomers once had to rely on more limited, more localized observations, Gaia has provided an extraordinarily detailed, galaxy-wide map of how stars are moving, allowing researchers to spot subtle patterns and connections that would have been nearly impossible to detect before. By studying globular clusters, stellar streams, and small satellite galaxies not as separate, isolated puzzles, but as interconnected pieces of the same underlying history, astronomers have been able to identify mergers that had previously gone entirely unnoticed. And the results of this approach have been genuinely striking. Fact 48 tells us that one recent Gaia-based study found evidence for 5 previously known mergers, plus one newly discovered merger, plus hints of a possible 7th. 5 confirmed. 1 newly discovered. And hints of yet another, still uncertain, still waiting for further evidence before it can be confirmed. It's a wonderful illustration of just how active this field of research remains today. Even with everything astronomers have already pieced together, about Gaia Enceladus, about Pontus, Sequoia, the Kraken, Heracles, and all the others, there remain new threads still being uncovered, new evidence still emerging, thanks to increasingly precise and increasingly comprehensive datasets like the one Gaia continues to provide. This leads naturally into Fact 49, which speaks to just how rigorous and precise this modern research has become. Modern studies now use extremely precise stellar ages, combined with the identification of counter-rotating stars, moving opposite to the galaxy's main rotation, to place genuinely tight limits on how the Milky Way formed and evolved over time. This precision matters enormously. Earlier generations of research often had to rely on broader, less certain estimates. But by combining detailed stellar ages with subtle patterns of orbital motion, researchers today can constrain not just whether a particular merger occurred, but roughly when it occurred, how large the merging galaxy likely was, and how it reshaped the structure of the Milky Way in its aftermath. It transforms this entire field from a collection of intriguing possibilities into an increasingly precise, increasingly well-supported scientific picture. And finally, as we bring this segment gently toward its close, Fact 50 offers something a little different from everything else we've discussed, a sense of relative calm, settling in after all this ancient turbulence. The Milky Way has been relatively quiet for the last 8 billion years, with no further encounters involving major galaxies during that entire span of time. 8 billion years of relative peace. After the dramatic, formative chaos of its early history, Gaia, Enceladus, Heracles, Pontus, Sequoia, the Kraken, and so many smaller streams and remnants besides, the Milky Way has spent the majority of its more recent history in a comparatively settled state. No further major galactic collisions. No further dramatic reshaping of its fundamental structure. Just the slow, steady turning of a galaxy that has already absorbed, and gradually calmed from, an extraordinarily eventful youth. Of course, relatively quiet, in galactic terms, still leaves room for smaller encounters. Sagittarius, still drifting through even now, and the ongoing, gentle formation of new stellar streams. But compared to the dramatic, structure-defining collisions of its deep past, the Milky Way's more recent history has been, by comparison, a long, gradual settling. A galaxy easing, gently, out of its turbulent youth, into the calmer, quieter rhythm we find ourselves within today. We've reached the halfway point of our journey together tonight, and it's remarkable to look back at everything we've covered. A galaxy slowly running low on the raw material for new stars. A wider universe experiencing that same gradual slowdown all around us. And beneath it all, a deep, layered history of ancient collisions. Gaia, Enceladus, Pontus, Sequoia, the Kraken, Heracles, Loki, and still more waiting quietly to be discovered, each one leaving its own quiet signature, still readable today in the motions of stars scattered throughout the sky above you. In our next segment, we'll continue this journey forward, moving from this deep, ancient history toward a new part of the story, beginning to explore other forces at work in the galaxy's slow evolution, as this long night of listening continues. For now, let yourself rest in this newfound quiet, a galaxy that has lived through so much turbulence, so much collision and change, now turning gently, calmly, above you, carrying its ancient history softly forward, into the stillness of these last 8 billion peaceful years. We've spent a good while now looking backward, tracing the Milky Way's ancient collisions and slow accumulation across billions of years. But something interesting emerges when we look even more closely at that history, a discovery that reshapes how we think about the galaxy's decline itself. Because it turns out this may not be the first time our galaxy has faced a slowdown quite like the one we described at the very beginning of this journey. The Milky Way star formation may have already experienced at least one major slowdown in its past, long before the gradual decline it's experiencing today. This is a genuinely striking idea. When we began this journey, we spoke of the Milky Way's decline as something unfolding now, in this current era, the long, slow tapering of star birth as the galaxy's gas reservoir gradually depletes. But evidence increasingly suggests that this may not be an entirely new phenomenon for our galaxy. It may have happened before. Not in exactly the same way, perhaps, but in a way that rhymes with what we're witnessing today. Fact 52 offers more specific detail. Evidence suggests the galaxy may have stopped forming stars altogether for a period of time, somewhere around 8 billion years ago, before star formation eventually restarted, though at a noticeably lower rate than before. Try to picture that. A pause. Not a slowdown, but an actual halt. An era in which the vast machinery of star birth across our galaxy went largely quiet, before eventually, gradually, sputtering back to life. It's a remarkable thing to consider, especially set against everything we discussed in our last segment, that ancient turbulent period of mergers and bursts of star formation, followed by roughly 8 billion years of relative calm. This pause appears to sit right around that same transition, as if the galaxy, after its chaotic youth, needed a kind of pause. A breath. Before settling into the steadier, quieter rhythm that has defined it ever since. The evidence for this comes from a particular set of astronomical observations. Fact 53 tells us that apogee, a survey designed to study the detailed chemical compositions of stars throughout the galaxy, provided important evidence that the Milky Way may have undergone exactly this kind of quenching episode in its past. By carefully measuring the chemical fingerprints locked within the light of hundreds of thousands of stars, spread throughout the galaxy, astronomers using apogee data were able to detect a curious gap, a kind of missing generation, evidence pointing toward a period where star formation appears to have significantly dropped off, or paused entirely, before resuming again afterward. It's a bit like examining tree rings and finding a stretch where growth seemed to stall almost completely, only to pick back up again in the years that followed, a quiet interruption, preserved in the chemistry of stars, long after the event itself. This idea, that the Milky Way has already lived through something resembling a partial death and rebirth, adds a fascinating layer of depth to everything we've been exploring tonight. Perhaps a galaxy's decline isn't always a single, one-way journey toward quiet. Perhaps, at least sometimes, there can be a pause, and then, remarkably, a second chapter. Let's shift our attention now to a different kind of geography, not through time, but through space, examining exactly where within the Milky Way today, star formation is still meaningfully occurring. Fact 54 tells us that recent age mapping studies suggest the Milky Way's active star-forming disk has a boundary, somewhere around 35 to 40,000 light-years from the galactic center. This is a wonderfully concrete piece of information. It means the galaxy's ongoing star birth isn't spread evenly across its entire vast structure. It's concentrated, largely, within a defined region, an inner zone where conditions remain suitable for gas to collapse and form new stars. Beyond that boundary, roughly 35 to 40,000 light-years out, the pace of active star formation drops away sharply. And what exists beyond that boundary is quite interesting in its own right. Fact 55 tells us that beyond this active boundary, many of the stars found out there are likely migrants, stars that drifted outward from somewhere closer to the galaxy's center, rather than having been born in that outer region themselves. This is a lovely, slightly unexpected idea. We often assume that a star exists wherever it was born, quietly living out its life in more or less the same region of the galaxy. But it turns out that stars can migrate, gradually drifting outward from their birthplace over long stretches of time, nudged by gravitational interactions with spiral arms or other structures within the disk. So a star found far out in the Milky Way's quieter outer reaches may, in fact, have been born much closer to the galactic center, long ago, before slowly wandering outward across billions of years, like a traveler who left home in youth and has spent a long, quiet lifetime drifting steadily further and further away. Now, you might assume that the very center of the galaxy, with its dense concentration of gas and dust, would be the most productive region for forming big, massive stars. But Fact 56 offers a genuinely counterintuitive correction to that assumption. The Milky Way's core is not necessarily the most efficient place for making massive new stars, despite having plenty of dense gas and dust available. It seems almost paradoxical at first. More raw material should mean more star formation, shouldn't it? But the galactic center is an unusual, extreme environment, and abundance of material doesn't automatically translate into efficient star birth. Conditions there are far more chaotic, far more energetic, than in the calmer, more orderly spiral arms further out, and that chaos can actually work against the delicate process required for a cloud of gas to collapse smoothly into a new star. Fact 57 explains part of the reason why. Extreme conditions near the supermassive black hole at the very center of the galaxy may actively suppress the birth of the biggest, most massive stars. At the heart of the Milky Way lies Sagittarius A star, an enormous supermassive black hole, surrounded by intense gravitational forces, powerful magnetic fields, and turbulent, rapidly moving gas. These extreme conditions create an environment that is, in many ways, actively hostile to the quiet, gradual collapse required for star formation. Gas near the black hole tends to be sheared apart by powerful tidal forces, or heated and stirred by intense radiation, rather than being allowed to settle calmly and cool into the dense, stable clumps needed to form new stars. So even though the galactic center holds an enormous quantity of gas, that gas often exists in a state that resists, rather than encourages, the birth of new stars, particularly the largest, most massive ones. It's yet another beautiful illustration of an idea we touched on earlier in this journey. Simply having gas isn't enough. The conditions of that gas, whether it's calm or turbulent, cool or superheated, matter just as much as its raw quantity. Now, let's look forward again, gently, toward where all of this might be leading. Fact 58 offers a thoughtful projection about the Milky Way's future. If this long decline continues along its current trajectory, the galaxy may become increasingly dependent on rare events, like gas infall from outside the galaxy, or future mergers, simply to keep forming stars at all. This paints a quiet, patient picture of the galaxy's likely future. As its own internal gas reservoir continues thinning, ordinary, self-sustained star formation may become harder and harder to maintain. And so, the Milky Way may increasingly come to rely on occasional infusions from outside itself, fresh gas drifting in from intergalactic space, or perhaps another small galaxy, wandering too close, and being drawn in, its own gas reservoir merging with what remains of the Milky Way's own. Fact 59 reinforces this idea directly. The Milky Way can be replenished, at least partially, by mergers with dwarf galaxies, which bring with them fresh reservoirs of gas and additional stars. This is, in many ways, a hopeful note tucked within an otherwise gradual story of decline. The galaxy's fate isn't entirely sealed by its own internal reservoir alone. External encounters, much like the ancient mergers we spent so much time exploring earlier in tonight's journey, remain a genuine possibility for the future as well, capable, potentially, of injecting new life, new fuel, new stars, into a galaxy that might otherwise continue quietly fading on its own. And this brings us, gently, to one particular encounter looming somewhere in the Milky Way's distant future, one that many of you listening tonight may have already heard mentioned before, even if only in passing. Fact 60 tells us that the Milky Way is currently moving toward the Andromeda Galaxy, at a speed of roughly 400,000 kilometers per hour, though this motion does not necessarily guarantee that a direct collision will occur. 400,000 kilometers per hour. An almost incomprehensible speed, and yet, across the vast, empty distances of intergalactic space, even this remarkable velocity translates into a journey that will take billions of years to complete. Andromeda, our galaxy's nearest large neighbor, has been drifting closer to the Milky Way for a very long time, drawn in by the mutual gravitational pull between our two galaxies. And yet, despite this steady approach, astronomers are careful to note that a direct collision isn't entirely guaranteed. The precise trajectories involved leave room for genuine uncertainty about exactly how this ancient dance between our two galaxies will ultimately unfold. We'll spend more time with Andromeda later in this journey, exploring exactly what astronomers currently understand about this looming, distant possibility. But for now, it's worth simply sitting with the image itself, two enormous galaxies, each containing hundreds of billions of stars, slowly, patiently drawing closer together across an ocean of intergalactic space, the culmination of a journey that began long before either galaxy's current inhabitants existed, and won't conclude until long after we're gone. We've covered a great deal in this segment, a possible ancient pause in the Milky Way's own star formation, echoing the very decline we've been exploring all along, a clearer picture of exactly where in the galaxy star formation still meaningfully continues, the surprising inefficiency of the crowded galactic center, and a first, gentle glimpse of Andromeda, drifting steadily closer across the dark. In our next segment, we'll continue following this story forward, carrying these threads with us as we explore even more of what the future may hold for our galaxy, and for the ancient, patient dance still unfolding between the Milky Way and its nearest great neighbor. For now, let yourself rest in the quiet immensity of it all, a galaxy that has paused before, and grown again before, now drifting steadily toward another vast island of stars, 400,000 kilometers every hour, unhurried, inevitable, somewhere out there in the dark. Let's stay with Andromeda a while longer, because the story surrounding this looming encounter has been changing quite a bit in recent years, and it's a genuinely fascinating shift to walk through slowly. For a long time, the collision between the Milky Way and Andromeda was treated almost as a certainty, a foregone conclusion, destined to unfold billions of years from now, regardless of anything else happening in between. But that old inevitable crash story is now being revised. And it's being revised specifically because of fresh data, gathered by missions like Gaia and Hubble, which have allowed astronomers to build far more complete and far more accurate models of exactly how these two galaxies are moving through space. This is worth appreciating on its own. Science, done carefully, is always willing to reconsider its conclusions when better evidence becomes available. And in this case, more precise measurements of position, motion, and mass, gathered patiently over recent years, have opened up a genuinely different picture of what might lie ahead. Fact 62 captures just how significant this shift has been. Recent NASA-led analyses now describe the Milky Way's future as completely open, meaning the best available data currently allow for very different outcomes, rather than pointing confidently toward just one. Completely open. It's a striking phrase, especially after everything we've discussed so far tonight. This idea that the Milky Way's long-term future, at least regarding Andromeda, isn't a settled matter at all. The old assumption that a collision was simply a matter of time has given way to something more nuanced, more uncertain, and in its own way, more honest. So what does the newer data actually suggest? Fact 63 tells us that new simulations propose the Milky Way and Andromeda may not definitely collide at all. Instead, there may be something closer to a 50-50 chance of an eventual merger, occurring sometime within the next 10 billion years. A coin flip. That's essentially what current models suggest when it comes to whether these two great galaxies will eventually merge. Not a certainty stretching confidently into the deep future, but something closer to genuine uncertainty, two plausible outcomes, roughly equally likely, based on our current best understanding. Facts 64 and 65 echo this same figure from slightly different angles, and it's worth hearing it more than once, because it represents such a meaningful departure from the old narrative. Recent studies suggest the Milky Way may have only about a 50% chance of merging with Andromeda within the next 10 billion years. And phrased the other way around, there is roughly an equal 50% chance that no such merger will occur at all, within that same span of time. It's remarkable, isn't it, to sit with the idea that something so often described, in documentaries and articles alike, as an inevitable cosmic event, may, in truth, be closer to an open question. Two possible futures, each roughly as likely as the other, and we simply don't yet know, with confidence, which one awaits. Interestingly, though, even within this newer, more uncertain picture, there's an important detail about timing worth pausing on. Fact 66 tells us that one result suggests the probability of a collision occurring within the next 5 billion years specifically, is quite low, only about 2%. 2%. This is a meaningful detail, because it tells us that even in scenarios where a merger does eventually happen, it likely wouldn't occur particularly soon, in cosmic terms. Most pathways toward a merger, according to this analysis, appear to unfold later, beyond that 5 billion year mark, rather than within it. Which means that even under the more dramatic possible future, there remains an enormous stretch of time, billions of years, before anything resembling an actual collision would begin to take shape. So why has this picture become so much more uncertain, compared to the confident predictions of years past? Fact 67 offers an important piece of the explanation. The uncertainty doesn't come only from the basic orbital motion of the two galaxies. It also comes from imperfect knowledge of the galaxy's precise positions and precise masses, both of which remain genuinely difficult to measure with complete accuracy, even today. It's easy to assume that astronomers simply know exactly where Andromeda is, and exactly how much mass it contains, and exactly how the Milky Way is moving in response to its gravitational pull. But measuring these things across such enormous distances, with the precision required to model an interaction unfolding across billions of years, remains an extraordinarily delicate task. Small uncertainties in these measurements, when projected forward across such a vast span of time, can lead to meaningfully different predicted outcomes, which is exactly why the picture has shifted from apparent certainty to a more honest, more careful acknowledgement of genuine uncertainty. Fact 68 expands on this a little further, describing specifically what factors continue to drive that uncertainty. It's driven by improved, but still imperfect, measurements of the galaxy's positions, their motions, and their masses, combined with the additional gravitational influence of other members of what astronomers call the local group, the broader collection of galaxies, including the Milky Way and Andromeda, bound loosely together by gravity across a relatively nearby region of the universe. This is an important addition to the picture. The Milky Way and Andromeda aren't moving through empty space in complete isolation from one another. They exist within a wider gravitational neighborhood, surrounded by numerous smaller galaxies, each exerting its own small, but potentially significant, gravitational influence on the overall dynamics of the system. And accounting for all of these subtle influences, accurately, adds yet another layer of complexity to any attempt at predicting exactly how this story will unfold. One particular member of that local group, though, appears to play an especially significant role in this story. Fact 69 introduces it directly. The Large Magellanic Cloud, a smaller companion galaxy currently orbiting the Milky Way, may play a major role in altering our galaxy's future orbit, and its gravitational influence may actually make a full merger with Andromeda less likely than it might otherwise be. The Large Magellanic Cloud is a modest galaxy compared to giants like the Milky Way or Andromeda, but it is far from negligible in terms of mass, and it currently orbits relatively close to our own galaxy. Its gravitational pull, subtle as it might initially seem, appears capable of exerting a genuinely meaningful tug on the Milky Way's overall trajectory through space. A tug significant enough, according to recent modeling, to shift the broader dynamics of the entire system, potentially steering the long-term relationship between the Milky Way and Andromeda away from a direct collision. Fact 70 reinforces this same idea, and it's worth letting it settle fully, given how central it has become to this revised understanding. The Large Magellanic Cloud strongly affects the overall Milky Way and Andromeda orbital dynamics, and its influence appears to make an eventual merger less likely than earlier, simpler models had once suggested. There's something quietly beautiful in this detail, if you sit with it for a moment. A relatively small companion galaxy, orbiting quietly and unassumingly around our own, may ultimately hold real influence over one of the grandest, most dramatic events imaginable, the potential merger of two entire galaxies, each containing hundreds of billions of stars. It's a lovely reminder that even in the vast, seemingly deterministic dance of galaxies moving through space, small players can matter, there's subtle gravitational nudges accumulating, over billions of years, into genuinely significant shifts in an otherwise grand and sweeping story. So where does all of this leave us, as we bring this segment toward its close? The old, confident narrative of an inevitable, foretold collision between the Milky Way and Andromeda has given way to something more genuinely uncertain, and in many ways, more honest. Roughly a 50% chance of an eventual merger, sometime within the next 10 billion years. A quite low probability, only around 2%, of that collision occurring anytime soon, within the next 5 billion years specifically. And a whole web of contributing factors, imperfect measurements, the combined gravitational influence of the wider local group, and the surprisingly significant role of a smaller companion galaxy, all combining to make this one of the more genuinely open questions remaining in our understanding of the Milky Way's long-term future. In our next segment, we'll continue to sit with this uncertainty a while longer, exploring a little more of what the different possible futures might actually look like for a galaxy that may, or may not, one day merge with its grand neighbor across the dark. For now, let this open question rest gently in your mind. Two vast galaxies, drifting slowly toward one another across an ocean of stars and time, their fate still genuinely unwritten, still balanced, delicately, somewhere close to the turn of a coin. We ended our last segment with the Large Magellanic Cloud, quietly tugging the odds of a merger downward. But it turns out there's another player in this story, one that pulls in exactly the opposite direction. M33, the Triangulum Galaxy, can also change the probability of a future merger, but in the opposite direction from the Large Magellanic Cloud. Triangulum is the third largest member of our local group, smaller than both the Milky Way and Andromeda, but substantial enough to matter in these calculations, and it appears to be gravitationally bound to Andromeda itself, orbiting it much the way the Large Magellanic Cloud orbits the Milky Way. And its presence in these models produces a genuinely different effect on the overall dynamics of the system. Fact 72 makes this contrast explicit. M33 affects the Milky Way and Andromeda's orbital dynamics in the opposite way to the Large Magellanic Cloud, and its gravitational influence appears to increase the probability of an eventual merger, rather than decrease it. So here we have two smaller companion galaxies, each exerting real gravitational influence over this grand, slow dance between the Milky Way and Andromeda, and each pulling the odds in a different direction. The Large Magellanic Cloud, nudging things toward a miss. Triangulum, nudging things toward a collision. It's a bit like two quiet voices offering different counsel on the same uncertain question, both worth listening to, neither one decisive on its own. This tug-of-war between competing influences helps explain, in part, why the overall picture remains so genuinely open. But it turns out these companion galaxies aren't even the largest source of uncertainty in this story. Fact 73 brings us to what astronomers currently consider the single biggest unknown of all. The biggest remaining uncertainty in the Milky Way's future merger with Andromeda is Andromeda's sideways motion, what astronomers call its transverse velocity. This is a subtle but important distinction. When we talk about Andromeda approaching the Milky Way at roughly 400,000 kilometers per hour, we're describing its motion along the line directly between the two galaxies, its approach speed, essentially, moving closer to us. But galaxies, like almost everything else in motion through space, don't necessarily travel in a perfectly straight line toward their target. There can also be sideways motion, a drift perpendicular to that direct approach, and it's this sideways component, Andromeda's transverse velocity, that remains genuinely difficult to measure with precision, even with today's remarkably advanced instruments. And this uncertainty matters enormously. Fact 74 makes clear just how sensitive the outcome is to this single measurement. Even a small change in that sideways motion can decide whether the two galaxies ultimately merge, or simply pass each other by. Picture it this way. Imagine two people walking toward each other across a vast, open field, each one approaching from a great distance. If they're walking directly toward one another, they'll eventually meet. But if either one drifts even slightly off that direct line, sideways, the two paths might miss each other entirely, passing by at some distance, never actually meeting at all. Now imagine that field stretching across millions of light years, and that sideways drift being almost impossibly small to measure from here, and you begin to understand why this single factor, Andromeda's transverse velocity, carries so much weight in determining the Milky Way's ultimate fate. Given how much hinges on this one measurement, it's worth understanding fact 75 a little more closely. Some newer models still allow for a genuinely high probability of merger, but the specific range of outcomes depends very strongly on the exact proper motion values used in each particular study. Proper motion, in this context, refers to the precise, tiny sideways shift of Andromeda's position across the sky, measured over time. And because this value is so difficult to pin down with complete confidence, different research teams, using slightly different measurements or slightly different assumptions, can arrive at genuinely different conclusions. Some models lean toward a higher probability of eventual merger. Others, as we discussed in the previous segment, land closer to that 50-50 split. The range of outcomes isn't a sign of sloppy science. It's an honest reflection of just how sensitive this whole system is to a measurement that remains, for now, right at the edge of what our best instruments can achieve. So what would it take to resolve this uncertainty more definitively? Fact 76 offers a genuinely hopeful, forward-looking answer. Future measurements, with uncertainties reduced to below about 2 microarcseconds per year, may be needed to finally pin down the Milky Way's merger fate with real confidence. A microarcsecond is an almost unimaginably small unit of angular measurement. It would take literally thousands of them, side by side, just to span the tiniest fraction of what the human eye could ever hope to distinguish. And astronomers are talking about measuring Andromeda's sideways drift across the sky with a precision finer than 2 of these vanishingly small units per year. It's an extraordinary technical challenge, sitting right at the frontier of what's currently possible, and future missions, building on the foundation already laid by Gaia, may eventually be capable of achieving exactly this level of precision, finally settling a question that has remained genuinely open for years now. In the meantime, though, it's worth sitting with what the current range of simulated outcomes actually looks like. Fact 77 paints a genuinely peaceful picture for many of these possible futures. In many simulated scenarios, the two galaxies miss each other widely, and simply continue evolving, mostly undisturbed, for a very, very long time. Widely. Not a near miss, not a close graze, but a genuine, comfortable distance. In many of these modeled futures, with the Milky Way and Andromeda continuing along their own separate paths, each one carrying on with its own long, slow story, largely independent of the other. Fact 78 reinforces this same picture from a slightly different angle. Most of the simulated outcomes that don't result in a merger show the two galaxies passing so far apart from one another that they continue evolving largely undisturbed, each one left to follow its own separate, quiet path through the vast dark of intergalactic space. There's something almost gentle in this image, isn't there? After everything, after this long, careful examination of possible collision courses and uncertain trajectories, a substantial portion of the possible futures simply involve nothing dramatic at all. Two galaxies, continuing to drift through the same general region of space, near one another in a cosmic sense, but never actually meeting. Each continuing its own long story, side by side, but separate. And what might that particular future look like, for the Milky Way specifically? Fact 79 offers a thoughtful answer. If the Milky Way misses Andromeda entirely, it may instead continue evolving more quietly, and may spend a much longer stretch of time in that slow, gradual fading state we spent so much of tonight's earlier segments exploring. In this scenario, without the dramatic disruption and eventual fresh burst of activity that a full galactic merger might bring, the Milky Way would likely simply continue along the path we described at the very beginning of our journey together, its gas supply gradually thinning further, its rate of star formation continuing to ease downward, generation after generation, star by star, settling ever more deeply into that long, graceful decline. Not an ending exactly, but an extended, undisturbed continuation of the quiet fading already well underway. As we bring this segment to its close, it's worth pausing on Fact 80, which offers perhaps the clearest, most honest summary of everything we've explored across this stretch of our journey together. Even if a merger with Andromeda does eventually happen, it is no longer treated, by researchers today, as a guaranteed outcome. The future of our entire local group, the Milky Way, Andromeda, Triangulum, the Large Magellanic Cloud, and all the smaller galaxies bound loosely together around them, is now considered, quite genuinely, dynamically uncertain. It's a remarkable place to arrive, after so much careful study, so much painstaking measurement, so many decades of assuming a collision was simply inevitable. The honest answer, today, is that we genuinely don't know. Two possible futures, each resting on measurements so delicate they sit at the very edge of what our finest instruments can currently detect. A sideways drift, smaller than almost anything else we've discussed tonight, quietly holding the answer to one of the grandest questions imaginable, whether our galaxy will one day merge with its nearest great neighbor, or simply continue drifting past it, into the long, undisturbed dark. In our next segment, we'll carry this sense of open possibility forward with us, continuing to explore what the Milky Way's future may hold, whichever path it ultimately follows. For now, let yourself rest in this beautifully unresolved question: two ancient galaxies, drifting through the dark toward a future that remains, even now, genuinely unwritten, their fate still turning, quietly, on a measurement too small for the eye to ever see. Let's linger a while longer in this uncertain future, because even within that genuine uncertainty, there remain a range of specific possibilities worth exploring, different timelines, different outcomes, each one still living within the range of what current science considers plausible. Fact 81 reminds us that some calculations still leave open a small chance of a direct, head-on collision occurring in just 4 to 5 billion years, closer, in other words, to that older estimate many of us may have heard before. It's worth holding on to this alongside everything we discussed in the previous segment. Even though the newest, most comprehensive modeling suggests something closer to a 50-50 split, spread across a much longer window of up to 10 billion years, a smaller slice of that overall range of possibilities still points toward a more traditional, nearer-term collision. Not the most likely outcome, according to current understanding, but not entirely ruled out either. Science, done honestly, tends to leave room for these kinds of residual possibilities, rather than closing the door on them completely. Interestingly, though, many of these simulated futures don't necessarily involve a single, decisive encounter. Fact 82 tells us that in many simulations, the Milky Way and Andromeda experience at least one close encounter, a near approach, before any eventual full merger actually takes place. This adds a fascinating layer of texture to the story. Rather than the two galaxies simply approaching once, colliding, and merging in a single dramatic event, many models suggest something more gradual, more layered, an initial close pass, gravity pulling the two galaxies together, disturbing each other's structure, before they swing apart again, only to be drawn back together, later, for a second, perhaps final, encounter. It's less like a single head-on crash, and more like a slow, repeated dance, gravity drawing the partners closer with each pass, before, eventually, in many scenarios, drawing them fully together. Given this more nuanced picture, when exactly might a full merger, if it happens at all, most likely occur? Fact 83 offers an updated estimate. If a collision does happen, the most likely timing may fall somewhere around 7 to 8 billion years from now, rather than the older estimate of 4 to 5 billion years that many people have heard for years. This shift in timing matters. It means that even in scenarios where a merger does eventually occur, current modeling tends to push that event further into the future than earlier estimates once suggested, giving the Milky Way, in most of these scenarios, a considerably longer stretch of relatively undisturbed time before anything resembling a genuine collision would begin to unfold. And some models push that timeline further still. Fact 84 tells us that certain scenarios place a full merger somewhere between 8 and 10 billion years into the future, rather than sooner. 8 to 10 billion years. To offer some grounding for that number, that's comparable to the entire age of the universe as it currently stands. Which means that in these particular scenarios, the eventual merger between the Milky Way and Andromeda wouldn't occur until roughly another full age of the universe has passed, measured from today. It's an almost dizzying stretch of time to hold in the mind, and it reinforces, once again, just how much room and how much time remains, in nearly every version of this story, before anything resembling a true collision would actually begin. Should a collision eventually occur, though, whatever timeline it follows, what would it actually look like? Fact 85 offers a wonderfully vivid image. A future collision, if it happens, could scatter stars into entirely new orbits, much like cosmic billiard balls, deflected and redirected by the encounter. It's a lovely, almost playful way to picture something so vast. Despite containing hundreds of billions of stars each, actual collisions between individual stars, during a galactic merger like this, would remain exceedingly rare. The distances between stars, even within a densely packed galaxy, are simply too vast for direct impacts to be common. Instead, what happens is more gravitational, each star's path gently, or sometimes dramatically, redirected by the changing gravitational landscape created as two entire galaxies pass through and around one another. Stars wouldn't crash into each other so much as get gently, or sometimes forcefully, nudged onto entirely new trajectories, swept into new orbits, scattered like billiard balls across a table vastly larger than anything we could ever truly picture, guided not by direct contact, but by the quiet, powerful pull of gravity itself. And this process, should it unfold, wouldn't simply reshuffle existing stars. It would also, according to Fact 86, spark something new. The Milky Way and Andromeda, when and if they begin merging, are expected to trigger an entirely new era of mixed star formation, a fresh burst of stellar birth, drawing on gas from both galaxies combined, before the newly merged system eventually ages, once again, into quiet. This echoes something we touched on much earlier in tonight's journey, the idea that mergers, disruptive as they are, often bring fresh fuel with them, triggering renewed bursts of star formation even as they reshape a galaxy's existing structure. A merger between the Milky Way and Andromeda, should it occur, would likely follow this same pattern, on an even grander scale, combined gas reservoirs from both galaxies mixing together, triggering a new, vigorous chapter of star birth, before the newly combined system, having exhausted this fresh supply, eventually eases into its own long, quiet decline, much like each individual galaxy has already been experiencing on its own. What would the two galaxies actually become, though, if they do eventually merge completely? Fact 87 offers a clear answer. During the merger, the two galaxies are expected to gradually transform into a giant elliptical galaxy, rather than remaining two separate, recognizable spirals. This represents a genuine transformation in fundamental structure. Spiral galaxies, like the Milky Way and Andromeda both are today, possess that elegant, rotating disk shape, with graceful spiral arms winding outward from a central bulge. Elliptical galaxies, by contrast, are smoother, more rounded, without the same organized rotational structure, their stars instead moving along more randomly oriented orbits, giving the whole galaxy a softer, more diffuse, egg-like or spherical appearance. A merger between two large spiral galaxies, like ours and Andromeda's, tends to thoroughly disrupt that elegant spiral structure, gradually reshaping the combined system into something closer to this smoother, rounder elliptical form, a genuinely different kind of galaxy altogether, born from the combination of two familiar spirals. Now, let's step back once more, and think even further into the future, beyond even this potential merger, toward the deepest, most distant stretches of time imaginable. Fact 88 offers an important, grounding reassurance. After the galaxy's major gas reserves are fully exhausted, Whether through this potential merger or simply through the continued slow decline we've discussed throughout tonight's journey, the galaxy will not simply vanish. It will persist, for an extraordinarily long time, as its existing stars continue to age, and eventually, individually, die. This is worth holding on to carefully. Running out of gas for new star formation doesn't mean the galaxy itself disappears. The billions upon billions of stars already formed, over the Milky Way's long history, will continue to exist, continue to shine, continue their own long, individual lives, for a very, very long time to come, even after the era of new star birth has largely come to its end. But not all stars age at the same pace. Fact 89 reminds us of an important distinction. The most massive stars will disappear first, in this far future, because they burn through their available fuel far more quickly than smaller stars do. This might seem paradoxical at first. Surely the biggest stars, with the most fuel available, would last the longest. But it doesn't work that way. Massive stars burn through their fuel at an enormously accelerated rate, blazing brilliantly, but briefly, in cosmic terms, living lives that might span only millions of years, rather than billions. So as this far future unfolds, it will be the largest, brightest, most massive stars that fade first, their brief, brilliant lives concluding relatively early, even as countless smaller, dimmer stars continue quietly shining on. And this brings us to a genuinely beautiful closing thought for tonight's segment. Fact 90 tells us that smaller stars live dramatically longer than stars like our own Sun, meaning the Milky Way, remarkably, can remain faintly active for trillions of years, even long after most of its brightest, most massive stars have already gone dark. Trillions of years. It's a number that dwarfs almost everything we've discussed tonight, even the 11 or 13 billion years stretching back to the galaxy's earliest formation. The smallest, faintest stars, the quiet red dwarfs scattered throughout the galaxy, burn their fuel so slowly, so patiently, that they can continue shining, dimly but steadily, for a length of time that makes the entire current age of the universe look brief by comparison. Long after the brilliant giants have faded, long after any potential merger with Andromeda has settled into its own quiet aftermath, these small, patient stars will likely still be there, faint, steady, glowing softly in the dark, carrying the Milky Way's story forward, into a future almost too vast to properly imagine. We've traveled a long way in this segment, through the layered uncertainty of a possible Andromeda merger, through timelines stretching 7, 8, even 10 billion years into the future, through the gentle image of stars scattered like billiard balls across a newly forming elliptical galaxy, and finally, out into the almost incomprehensible future of trillions of years, where small, patient stars continue quietly glowing long after everything else has faded. In our next segment, we'll continue following this thread even further into that distant future, exploring what ultimately becomes of a galaxy, long after its era of vigorous star formation has drawn to its close. For now, let yourself rest in the scale of it all, a galaxy that may merge, or may simply drift past its neighbor undisturbed, either way continuing to shine, faintly, patiently, for a length of time that stretches so far beyond our own brief lives that it becomes, in the end, less a number, and more a kind of quiet, endless reassurance. We ended our last segment with those small, patient red dwarfs, still glowing quietly, long after the galaxy's brighter stars had faded. Let's stay with them a little longer, because they may hold the key to understanding just how extraordinarily long this final chapter of the Milky Way story could actually last. Red dwarfs can survive for a few trillion years, which means the Milky Way's final, dim phase, that long, quiet afterglow following the end of vigorous star formation, could stretch on for an extraordinarily long stretch of time indeed. A few trillion years. It's worth sitting with that number once more, letting it settle fully, because nothing else we've discussed tonight comes close to matching it. The current age of the universe, at roughly 13.8 billion years, is a small fraction, just a tiny sliver, of what a single trillion years even represents. And red dwarfs, these small, unassuming stars, dim and patient, burning their fuel so slowly and so efficiently, may continue shining softly for several such trillion-year spans, long after nearly everything else in the galaxy's more dramatic history has quieted completely. So what does the Milky Way actually become, across this almost unimaginable stretch of future time? Fact 92 offers a clear, if gentle, answer. In the very distant future, the Milky Way may become a dim, elliptical remnant, with very little star formation remaining at all, effectively, in the language astronomers sometimes use, a dead galaxy. It's worth pausing on that word, dead, for a moment, because it can sound more final, more stark, than what we've actually been describing throughout this entire journey. This isn't death in the sense of sudden absence, of darkness falling all at once. It's death in the sense of quiet completion, a galaxy that has finished the vast majority of its active star-forming life, its brilliant spiral structure long since reshaped by mergers, its remaining light coming mostly from small, dim, incredibly long-lived stars, still faintly glowing, scattered throughout what has, by then, likely become a smoother, rounder, elliptical shape. Within this distant future galaxy, there exists a whole population of stellar remnants, the quiet leftovers of stars that have already lived out their lives. In fact, 93 tells us something quite remarkable about what eventually happens to some of them. Some of these dead stellar remnants, within what astronomers sometimes call the galaxy's future galactic underworld, may eventually be ejected entirely, flung out into intergalactic space. The galactic underworld. It's an evocative phrase, isn't it? Conjuring images of a hidden, quiet population, drifting through the darker, less visible corners of the galaxy's structure. This underworld consists of the remnants left behind after stars complete their lives, dense stellar corpses, white dwarfs, neutron stars, and occasionally, black holes, scattered throughout the galaxy, no longer shining with the fusion-powered light of an active star, but still present, still gravitationally bound, at least for now, to the larger structure of the Milky Way. And it turns out that a genuinely significant portion of one particular type of remnant may not remain bound to the galaxy forever. Fact 94 gets specific. Around 30% of dead neutron stars, within this remnant population, may eventually be flung entirely out of the Milky Way's local environment altogether. Nearly a third. When a massive star reaches the end of its life and collapses into a neutron star, the process itself can be remarkably violent, often imparting a substantial kick to the newly formed remnant, sending it hurtling away from its original location at considerable speed. Over the galaxy's long history, and especially considering the additional disturbances caused by mergers and gravitational interactions across billions of years, a meaningful fraction of these neutron stars may end up with enough velocity to escape the Milky Way's gravitational hold entirely, drifting away, quietly, into the vast, dark emptiness of intergalactic space, carrying their dense, compact mass forward into a solitary future, far from the galaxy that once created them. Meanwhile, even as this process unfolds within the galaxy itself, something even larger is happening across the universe as a whole. Fact 95 brings us back, one final time, to that grand cosmic backdrop we touched on earlier in tonight's journey. In a very distant future, the universe's ongoing expansion will leave the Milky Way increasingly isolated from more distant galaxies. This is the same cosmic expansion we discussed much earlier, the one that gradually thins out gas and makes star formation more difficult across the universe as a whole. But its effects reach even further than that. As the universe continues expanding, the space between galaxies continues to stretch, and distant galaxies, over almost inconceivable spans of time, will gradually recede beyond our ability to observe them at all. The Milky Way, along with whatever remains of Andromeda, and the other nearby members of our local group, will eventually find itself increasingly alone, a small, isolated island of stars, adrift in an ever-emptier, ever-expanding universe. Even the most extreme, most seemingly permanent objects in the universe aren't entirely exempt from this long process of fading. Fact 96 offers a genuinely mind-bending thought to close out this part of our journey. Much later still, even black holes themselves are expected to eventually evaporate, through an extraordinarily slow process known as Hawking radiation. Black holes. Objects so dense, so gravitationally powerful, that not even light itself can escape their pull. And yet, according to our current understanding of physics, even these objects are not truly eternal. Over spans of time that make even the trillions of years we discussed earlier look almost brief by comparison, black holes are believed to slowly radiate away their mass and energy, through this subtle quantum process, gradually shrinking, and eventually, unimaginably far in the future, evaporating entirely. It's a genuinely humbling thought to sit with, that even the deepest, most seemingly permanent, most inescapable structures in the universe are subject to this same slow, patient process of fading. And so, as we gather together everything we've explored across this long, unhurried journey tonight, we arrive at Fact 97, a beautiful summary of everything this entire story has really been about. The galaxy's death, therefore, is not a sudden catastrophe. It is a gradual fading, unfolding across a span of time stretching from billions, all the way out to trillions of years. Not an ending, in the way we often imagine endings, not a single dramatic moment, a collapse, an explosion, a sudden darkness falling. But something far gentler, and in its own way, far more beautiful. A long, slow, graceful winding down. Gas reservoirs gradually thinning. Star formation gradually easing. Massive stars fading first, small stars persisting for almost unimaginable stretches of time afterward. Perhaps a merger with Andromeda along the way, reshaping everything into something new. Before that too, eventually, settles into its own quiet decline. And finally, across trillions of years, even the faintest embers slowly, gently, going dark, while the universe itself continues expanding around it, carrying the Milky Way's story forward into an isolation so complete, so vast, that words can barely capture it. It's worth remembering, as we near the very end of this long night together, that our understanding of this entire story continues to evolve. Fact 98 reminds us of this directly. Every new observation, from missions like Gaia, and from observatories continuing to study the sky in ever greater detail, continues refining our picture of exactly how this slow death will unfold. Everything we've explored together tonight, the ancient mergers, the uncertain fate of Andromeda, the long, slow fading still ahead, represents our best current understanding, built patiently, piece by piece, from careful observation and careful analysis. And that understanding continues to grow, continues to sharpen, with every new data set, every new measurement, every new generation of instruments turned patiently toward the sky. The story we've told tonight isn't a finished, final account. It's a living, evolving picture, still being refined, even now, by astronomers working quietly, patiently, to understand the galaxy we all call home just a little more clearly than we did before. And so, we arrive at fact 99, which brings together perhaps the two largest threads of everything we've explored across this entire journey. Whether Andromeda eventually revives the Milky Way through a dramatic merger, or simply passes it by, leaving it to continue its quiet fading undisturbed, the galaxy's long-term decline appears, in either case, ultimately unavoidable. There is something quietly peaceful in this thought, rather than something to fear. Whichever path unfolds, whichever version of the future actually comes to pass, the deep, underlying story remains essentially the same. A galaxy, born from primordial gas billions of years ago, that spent its early history growing through vigorous star formation and dramatic collisions, that built itself, layer upon layer, through both its own internal processes and the quiet absorption of smaller companions, and that is now, gradually, unhurriedly, easing into a longer, gentler chapter of its existence. Whether punctuated by one final, grand encounter with Andromeda, or simply continuing on its own quiet path alone, the destination, eventually, is the same. A slow, graceful fading, stretched across a span of time our minds can barely begin to hold. And this brings us, finally, to fact 100, the very last piece of tonight's long journey, and perhaps the truest, most gently reassuring thought of all. The slow death of the Milky Way is ultimately part of the slow aging of the universe itself. This is where we began, in a way, all those hours ago, and it feels fitting to return to it now, at the very end. The Milky Way story was never truly separate from the universe's own much larger story. Its early growth, its ancient mergers, its long, slow decline in star formation, its possible future with Andromeda, and its eventual fading into a dim, quiet remnant, all of it unfolds within, and because of, the same grand, patient aging process playing out across the entire universe. Every galaxy, everywhere, is living some version of this same story. Rising from primordial gas, building itself through fire and collision, reaching its own golden age, and then, slowly, gently, over spans of time too vast for any single mind to fully hold, easing into quiet. There is nothing to fear in any of this. Nothing urgent, nothing that touches your life, or the life of anyone you love, or even the life of our species, however long it may continue. This is simply what it means to exist within a universe defined by time so vast it becomes, eventually, less a measurement, and more a kind of quiet, patient poetry. Stars are born, and stars fade. Galaxies grow, through violence and gentleness alike, and galaxies, eventually, grow quiet. And somewhere within all of that vast, unhurried unfolding, here we are, tonight, briefly, wonderfully awake, looking upward into a sky filled with ancient light, light from stars that may already be gone, traveling toward us across distances and times we can barely comprehend, carried by a galaxy that has already lived through more than we could ever fully imagine, and that will continue on, fading softly, patiently, for longer than anything we could ever truly measure. The Milky Way above you tonight, turning quietly in the dark, carrying its 200 billion stars, its ancient fossils, its 90% of its original hydrogen supply already spent, its careful uncertain dance with Andromeda still unfolding somewhere in the deep future, is not simply a backdrop to your life. It is, in its own vast and unhurried way, a companion. A patient, ancient, endlessly fading companion, that will keep glowing softly, long after everything else in this story has settled into stillness. Let yourself rest now, in the quiet company of that thought. The galaxy above you has already lived through so much, and it has so very, very far left to go. Billions of years of gentle fading still ahead. Trillions of years of small, patient starlight still to come. And somewhere in all of that vast, unhurried time, you, right now, are simply here, for one small, brief, beautiful moment, beneath it all. Rest well. And let the slow, endless turning of the galaxy carry you gently, into the quiet dark ahead.